principles of turbo machinery are the preliminary design tools while designing a turbo machine. Let it be anything, an axial turbine, a centrifugal machine, or a Pelton wheel, you can predict performance of all of these, from same turbo machinery fundamentals. To develop turbo machinery fundamentals, consider fluid flow through this channel. The inlet velocity, V1 gets changed to outlet velocity V2. Velocity of fluid can be split into tangential and radial components. In order to make the fluid flow, there should be an external torque acting on it. This torque can be derived from Newton's second law of motion, which acts as fundamental equation of turbo machinery. The torque is given by this equation, which is also called as Euler turbomachine equation, the most important equation in turbo machinery. If the channel is rotating at an angular velocity omega, the power required to maintain the fluid flow will be torque multiplied by angular velocity. Omega into radius becomes channel velocity, or blade velocity. So, power required for this fluid motion can be taken as difference in product of blade velocity times tangential fluid velocity. V theta is positive if it is in same direction of blade velocity, otherwise it is negative. If we divide power by weight of fluid flowing, we will get what's the energy head required to maintain this flow. If power required by the fluid is positive, it means fluid is absorbing energy, or the device is acting as a compressor. Otherwise, fluid is losing energy, so the device acts as a turbine. V theta more precisely means component of fluid velocity, which is parallel to blade velocity. But determination of fluid velocity is a tricky affair in turbo machinery, since we are dealing with rotating components. For this purpose, we should understand concept of velocity triangles. The key idea in turbo machinery is concept of relative velocity. Suppose you are standing on this rotating turbo machine. The velocity of fluid you experience while moving with it is called as relative velocity. If fluid is having an absolute velocity v, and the blade is moving with a velocity u, then relative velocity experienced by you will be v minus u. For a stationary device, flow should be tangential to the blade, in order to have smooth operation. Similarly, in a moving device, relative velocity should be tangential to blade profile. You can rearrange this equation, and say U plus W is absolute fluid velocity. Similar velocity triangle can be made on inlet of turbo machine. The beauty of turbo machinery is that, using relatively simple analysis of inlet and outlet velocities, you can predict performance of any turbo machine. We will see how to predict performance of a centrifugal pump, using the concepts we developed. Here we have shown an impeller of a centrifugal pump. If you know the blade geometry, you can find out blade angle at inlet and outlet. Blade angle is defined like this, as angle opposite of blade velocity. So we can easily fix direction of relative velocity. Radial component of flow velocity determines how much is the volume flow rate leaving the impeller. So you can determine VR at outlet from this equation. Now construction of velocity triangle is easy, you can draw lines parallel to these velocity components. Absolute velocity of flow can be drawn like this. From this we can find out tangential component of flow velocity. At inlet of centrifugal pump flow velocity will be radial, so tangential component of velocity is 0. So energy head developed by the pump simplifies like this. Blade angle can be easily derived like this. You can easily substitute a value for V theta using these two equations. Finally we get most important performance equation of centrifugal pump. How energy head is varied with flow rate. We can predict performance of an axial flow device, and Pelton wheel, using the same concepts we developed before. You can check it on next video.